Imagine someone places a mysterious box in front of you. The box accepts a single bit, either 0 or 1, and always returns another bit as its answer. Surprisingly, there are only 4 possible behaviors this box can have. Our challenge is simple. Determine whether the box always gives the same answer, called constant, or gives different answers, called balanced.
A classical computer has no choice. To be certain, it must test both possible inputs.
One question simply isn't enough. The computer must ask twice to uncover the truth. Quantum mechanics offers an unexpected shortcut.
Deutsch's algorithm begins with 2 qubits prepared in carefully chosen states. Hadamard gates transform these qubits into superpositions, allowing them to explore multiple possibilities simultaneously. The mysterious box is now called an oracle. It hides the function we wish to investigate. Through superposition, the quantum computer effectively examines both possible inputs at the same time. The oracle leaves behind subtle phase information, invisible at first glance. Another Hadamard gate transforms those hidden phases into observable outcomes.
A single measurement now reveals whether the function is constant or balanced. Remarkably, the quantum computer solves the problem with only one query. This was the first algorithm ever proposed to demonstrate a genuine quantum advantage. The true power of Deutsch's algorithm comes from quantum interference, where probability waves combine to reinforce useful answers and eliminate the wrong ones.
Although phase cannot be measured directly, interference converts these hidden phase differences into information we can observe.
The oracle never reveals its secret directly. Instead, it subtly changes the quantum state, leaving behind clues encoded in its phase. Every step of the algorithm can be represented as a simple quantum circuit, guiding qubits through a carefully planned sequence of operations. Instead of checking every possibility one by one, quantum computation cleverly combines many possibilities before making a single measurement.
Although simple, Deutsch's algorithm became the first true quantum algorithm, inspiring decades of research into quantum computing.
Coherence times are holding.
Directing the next pulse now.
Deutsch's original idea soon evolved into the Deutsch algorithm. It is capable of solving much larger versions of the same problem.
More importantly, Deutsch's algorithm changed how scientists think about computation itself, showing that quantum mechanics could outperform classical logic.
What began as a simple thought experiment became the first step toward the quantum revolution, inspiring algorithms that continue to reshape the future of computing. By proving that one carefully prepared quantum query could replace 2 classical ones, Deutsch's algorithm revealed a new kind of computational advantage. From this simple idea grew an entire field of quantum algorithms, each exploring how superposition and interference can solve problems in extraordinary ways.
Deutsch's algorithm did more than solve a puzzle. It introduced the world to a new way of computing, one where the laws of quantum mechanics become the language of computation itself.